question 1221, we're asked to predict the product. In this screencast, we're going to look at parts A, B, and C. What you'll notice that in each of these problems, there's multiple steps. So again, in keeping with our strategy for solving these problems, we want to identify the major functional groups present in each of the starting materials. For part A, this group here is an alkene, and this group here is an ester. So remember that a carboxylic acid derivative with an alkyl group in place of the proton is called an ester. We're treating that with methyl magnesium bromide in excess. So that means there's a greater than 1:1 molar ratio of this to the starting material. In the second step, we're treating with ammonium chloride. So we need to recognize that that is a workup step. Since we're treating with an excess of methyl magnesium bromide, the first product will be addition of methyl carbanion to the ester. That is going to take the ester down to the ketone. We'll put in the remaining functional groups that are not participating in this reaction. So how does this happen? This is the Grignard reagent, methyl magnesium bromide. So if we recall from electronegativity arguments on the periodic table, the carbon is going to own the electrons in this bond. The magnesium bromide is just the cation for this anion. So since carbon owns these electrons, it's going to attack the ester. We know carbon can only have 4 bonds, so we're going to break this bond, the pi bond of the CO carbonyl group. That's going to form a tetrahedral intermediate that will collapse and eject out methoxide. Ultimately, we get the ketone. You'll notice that we're running this reaction with an excess of this reagent. So a second equivalent is available to attack that ketone. So the product of this step is going to be an alkoxide. So oxygen now bears the negative charge. The cation is going to be this magnesium bromide. And we'll fill in the rest of our non-participating functional groups. So at this step, we've taken an ester down to a tertiary alcohol. The ammonium chloride is simply there to convert the alkoxide into the alcohol. So it's a simple protonation event. In part B, again, we're going to identify the major functional groups. In this case, we have a vinyl bromide. We're treating that with magnesium metal, the C1 aldehyde, formaldehyde, and then we're going to do an aqueous acidic workup. Anytime we have a halogen and a magnesium metal, we're going to form a Grignard reagent. So the Grignard reagent is the formal name for an organomagnesium species. So we're forming this species in step number 1. you can think of it in the simplest sense of magnesium inserting into this carbon-bromine bond. Again, organometallic species, the carbon is going to bear the bulk of the electron density. It's making this carbon nucleophilic. In step 2, we're treating with formaldehyde. Formaldehyde is the simplest aldehyde. In this case, it's based on methanol, methanol being oxidized up to the aldehyde. Let's recall the structure or electron density distribution in a carbonyl. The oxygen is going to bear the bulk of the pi density. The carbon is going to be positive. We want to form a bond between negative and positive. We're going to make a carbon-carbon bond. So a bond has to break. That's going to be the CO pi bond. So the product from this step is going to be the alkoxide of a primary alcohol. So oxygen now bears the negative charge. The counter ion is magnesium bromide. So we've taken an aldehyde with a Grignard reagent to make a primary alcohol. So finally, the aqueous acidic workup simply protonates the alkoxide. In part C, again keeping with our strategy, we're going to identify the major functional groups present. In this case, we have a secondary alcohol. We're going to take this step by step. So in step 1, we're treating with phosphorus tribromide. So those are conditions that we need to recognize will transform or substitute an alcohol for a bromide. So we've gone from a secondary alcohol to a secondary bromide. We've now activated this carbon to insert that magnesium and make a Grignard reagent. So magnesium metal will insert. So again, this is a Grignard reagent. It's an organomagnesium species. This carbon here is bearing the electron density, so we can think of it as a carbanion. And then the final step, we're treating that with an acid. So if we draw out hydronium, this step is going to protonate that carbon. So our product is going to be the alkane. So this carbon now bears 2 hydrogens. So overall, what we've done in part C, we've deoxygenated this carbon. We've taken it from the alcohol oxidation state all the way down to the alkane. So we can think of this as a formal reduction using a 3-step process.